Introduction to Infinite Series. Objectives. By the end of this lesson, you should be able to define an infinite series, find a partial sum of an infinite series, explain how partial sums can be used to determine if an infinite series converges, and apply properties of infinite series. An infinite series is the sum of the terms in a sequence. So all the terms in a sequence are A1, A2, A3, A4, and so on. So we're adding up all of the terms in a sequence. And since the sequence goes on forever, we're adding up infinitely many terms. And we use that sigma notation from n equals 1, or the starting index, whatever it is, to infinity of a sub n. So last time we talked about a finite sequence, and it definitely makes sense to add up a finite number of numbers. But does it make sense to add up infinitely many numbers? Will you ever get a finite number? So is it possible to add infinitely many numbers and get out a finite result? So infinitely many numbers add up to a finite number. Does that make sense? Is that going to be true? Well, to think about this, let's take a look at the famous Zeno's paradox. Alright, so Zeno's paradox, or one of Zeno's paradox, and this is actually explained in many different ways, but I'm going to use the example of a man trying to get to a door. So, will this man ever be able to reach this door? So he can walk, and the distance from where he's currently standing to the door, let's go ahead and say that it is a distance of 1 unit away. So this whole distance here is 1 unit. We won't worry specifically about what those units are. Well, if he is going to walk the whole distance to the door, that 1 unit, he's definitely going to have to walk halfway there. So if he's able to walk the entire distance, well, then he must be able to walk half of the original distance. So 1 unit is going to be equal to definitely half of the unit, plus, well, he's going to also have to be able to walk half of the remaining distance. So from this current point at halfway to half of the remaining half. So now he is standing right here, and he's gone a quarter of the original way. So right now this 1 whole unit is equal to 1/2 plus 1/4, but from where he's at this point right here, this red version of him, well, if he's going to walk the whole way, he's going to walk another half of the distance that's remaining. So he's going to end up right here, another halfway, which is a total of 1/8 of the original full amount. So right now, 1 unit is equal to 1/2 plus 1/4 plus 1/8. And, well, if he's going to get all the way to the door, he's going to have to go another halfway. So let's go back to blue and say that he's going to have to go another halfway. So he's going to have to be right here. And that distance of the whole 1 unit is 1/16. So far we have that 1 unit is 1/2 plus 1/4 plus 1/8 plus 1/16 plus, well, he's going to have to go another halfway. If he's going to get all the way to the edge here, he's going to have to go another halfway. Somehow he's getting skinnier. He's going to have to go another halfway, which is a distance of 1/32, the original length. And so on and so forth. So is he ever going to reach the door? Absolutely, yes. He's definitely going to reach the door. He's going to go that entire 1 unit traveled. But notice that 1 unit was equal to 1/2 plus 1/4 plus 1/8. We can continue to divide those remaining portions in half and half and in half again. So 1 looks like it equals the sum of infinitely many terms. So it is possible to add up infinitely many terms and get out a finite number. So we just established that it is possible for infinitely many terms to be added together to get a finite number. Now when this happens, we say that the series converges. But this is actually a really complex concept. So in order to formally make sense of it, we need to define what's called a partial sum. So a partial sum is the sum of part of the infinite series. So suppose you have the infinite series given by the sum from n equals 1 to infinity of a sub n. Well, the fifth partial sum with the notation s sub 5 means that you're going to add together the first 5 terms of the sequence. So you're going to add A1 plus A2 plus A3 plus A4 plus A5. So what we're going to do is we're going to look at the sequence of partial sums to decide whether or not that sequence converges, and that will help us decide if the series converges. So there's a lot of parts going on right now. We're definitely going to look at some examples. Alright, in this first example, we're going to find the first 5 partial sums of the series, the sum from n equals 1 to infinity of 1 over n squared. So S1 means we're going to sum the first term only. So the first term is 1 over 1 squared. So 1 over 1 is just 1. The second partial sum means we're going to add the first 2 terms together. So I'm going to have 1 over 1 squared plus 1 over 2 squared. So now I'm substituting 2 into the n and adding the first 2 terms together. So I'm going to have 1 over 1 plus 1 over 4. So common denominators, this is 4 over 4. So this is 5 over 4. And now S3 means I'm going to add the first 3 terms. So 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared. Well, we already did 1 over 1 squared plus 1 over 2 squared. That was 5 over 4. So 5 over 4 plus, and then I'm adding 1 over 9. So what I'm going to do from here on is I'm actually going to do some decimal approximations and use my calculator. So 5 over 4, we don't need a calculator. That's 1.25. 5 over 4 plus 1 over 9 happens to be, and I'm going to round to the third decimal place here, 1.361. And then when I compute S4, well, S4 is going to be 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared. And if I actually go ahead and put all of that in my calculator, I'm going to get 1.424 if I round to the third decimal place. And then S5, so that's 1 over 1 squared, 1 over 2 squared, 1 over 3 squared, 1 over 4 squared, plus 1 over 5 squared. That's going to give me 1.464. And I'm actually going to go one further, although I'm not going to write it all out. So it's all of this plus 1 over 6 squared. That's going to give me 1.491. So I'm doing this because what I'm ultimately interested in is whether or not adding up all of these terms, infinitely many terms, given by the general term 1 over n squared, if I add all those numbers up, am I going to get to some finite number? Well, what we take a look at instead is the sequence of partial sums. So this is the first partial sum, the second, the third, the fourth, the fifth, and the sixth. So maybe it's nice if we write it out as a sequence inside curly braces. So 1, comma, 1.25, 1.361, 1.424, 1.464, 1.491, and on and on and on. So what we're looking at is whether or not we think this sequence converges, this sequence of partial sums. If this sequence converges, then we say that the original infinite series converges, and it converges to whatever the sequence of partial sums converge to. So hopefully it looks like to you that this is heading towards 1.5 or 3 over 2. And ultimately, we can't really tell. This is just an educated guess by looking at the sequence. But it is true that this sequence is going to converge to 3 over 2. So that means that this original series converges, and it converges to 3 over 2. So let's formalize this idea now, the convergence of an infinite series. If the sequence of partial sums, so S sub n, so the list of all the partial sums, if that sequence converges to some real number L, so if the limit as n approaches infinity of the sequence of partial sums converges to a real number, then we say that the original series converges, and the limit L is the sum of the series. Otherwise, we say the series diverges. So let's go ahead and try to take a look at another example of this. Alright, we want to compute several partial sums of the series until we can try to identify whether or not the sequence of partial sums converges. So the infinite series is n equals 1 to infinity of 1 over 2 to the n. So S1 is the partial sum that is just the first term. So 1 over 2 to the 1, which is just 1/2. Now S2 means we're adding the first two terms. So we're going to have 1 over 2 plus 1 over 2 squared. So 1 over 2 plus 1 over 4. So common denominators, that's 2 over 2, 2 over 4, plus 1 over 4, plus is 3 over 4. And then S3 is 1 over 2 plus 1 over 2 squared plus 1 over 2 cubed. That's 1/2 plus 1/4 plus 1/8. Well, 1/2 plus 1/4, we already did. That was 3/4. We're going to need common denominators with 1/8, so that's 6/8 plus 1/8, so that's 7/8. Now, S4 is going to end up being, well, it's going to end up being S3, so 7 over 8 plus 1 over 2 to the 4th, so 7 over 8 plus 1 over 16. 7 over 8 is going to end up being 14 over 16. So this is 15 over 16. So S5 is going to be S4, 15 over 16, plus 1 over 2 to the 5th. So 15 over 16 plus 1 over 32. So 15 over 16 is 30 over 32. So 31 over 32. So we've computed several partial sums. We ended up with 1/2, 3/4, 7/8, 15 over 16, 31 over 32 as our sequence of partial sums. So let's write it out horizontally. 1/2, 3/4, 7/8, 15 over 16, 31 over 32, and so on and so on. So hopefully we can notice here this is 1/2, and this is or 0.5 if we want to do decimals, 0.75. These are all getting closer and closer to 1. So this sequence of partial sums, this sequence is converging to 1. So that means that the original series converges to 1. And hopefully, maybe you might recognize this. This was the Zeno's paradox example that we did. So we had 1/2, 1/2 plus 1/4, 1/2 plus 1/4 plus 1/8. 1/2 plus 1/4 plus 1/8 plus 1/16, and so on. And so we said that that had to add up to equal 1 if 1 was that total distance traveled by the man. So this is the formal method of determining whether or not an infinite series converges or diverges. So now I want to kind of stop to talk about where we're going to be heading. So one of our major goals is going to be to determine whether or not a series converges or diverges. Now, just determining convergence or divergence is going to be tricky enough, and it's only going to be in really special cases that we will even be able to determine what the series converges or sums to if in fact it does converge. So we don't actually use that formal process of finding the limit of partial sums to determine convergence or divergence in the previous examples. So if in those last two examples you were thinking, well, this is kind of a lot of work, and we kind of just were hand-wavy about the fact that the first limit of partial sums got closer to 3 over 2, and the second limit of partial sums got closer to 1. Instead, we're actually going to use a collection of tests. And that's going to be the focus of the next several lessons, is using these different tests to find convergence or divergence of an infinite series. But before we do that, we're going to take a look at one quick theorem. So this is going to be about properties of convergent series. So let's say C is just some real number, and let's say we know that the infinite series of A sub n converges to A, and the infinite series of B sub n converges to B. Then, well, this first part of the properties tells us that we can pull a constant out of any infinite series. So the sum of C times A sub n, where C is a constant, is the same as C times the series of A sub n. And this infinite series converged to A, so this is just the same as C times A, the constant times the sum of the series. The second part of the property says that the sum of A sub n plus or minus B sub n, well, if we know that each of those individual series converge, then we could split it up into the sum of A sub n plus or minus the sum of B sub n. And this series, the first one converged to A and the second one converged to B, so this could be simplified to just A plus B. And the last one sounds trickier than it is. So the last one says for any positive integer k, the sum from n equals k to infinity of A sub n converges, but probably not to A. So what we know is that the sum from n equals 1 to infinity of A sub n converges. So let's expand this out. This would be A1 plus A2 plus A3 plus A4 plus dot 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 plus A sub k plus dot dot dot. Goes on forever. We know that this infinite sum equals a finite number and it equals A. Well, for any positive integer k, so we already know that this works for 1, which is a positive integer, so pick any other positive integer. Let's pick 3. So the sum from n equals 3 to infinity is also going to converge. So let's think about that. If all of the terms, a1, all the way out to infinity, if all of those add up to a finite number, well, if I sum n equals 3 to infinity, now I'm cutting off the first two parts. So a3 plus a4 plus dot 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 all the way out. Well, if I add up less than this amount of numbers, so I'm taking away a1 and a2, that's definitely going to converge as well. But it's going to converge to some different value. Let's call it m. So if I'm taking out two numbers from this collection of infinite numbers I'm adding together, well, I'm making it a smaller amount that I'm adding together, so it's still going to end up being a finite number, but I'm changing the terms that I'm adding, so it's not going to be the same finite number. So that's what it's saying. And that's an idea that's going to extend when we start talking about some of those tests that we're going to be using to determine convergence or divergence of a series.